Much better. All right, scholars, welcome back. So we're going to pick up and start to transition into content that I would say is a little bit more complex than what we've been working with. You might be sitting there saying, like, more complex. But we're going to take baby steps. So we're going to learn to model periodic phenomena with trigonometric functions. So I compare and contrast in writing the features of the cosine, sine, and tangent functions. It is very important that you memorize, define these first two words. Although I've got it when I understand that the graph of a periodic function can look like a wave whose outputs repeat between the same maximum and minimum values. So here we have a bouncing curve with the x-axis representing time and the y-axis representing the distance from the start line. Could be, actually, I'm not going to actually say what it could entail. Think of circular, can't bend this finger, circular behavior when describing what you notice and what you wonder. So we have a few graphs, and there's our one from the do now, that produce phenomena that have a repetitive nature. So describe the dependent and independent variable. Remember, the dependent variable is what we would consider the output, and the independent variable is what we would consider the input, because the input is what we can alter. The output is contingent upon the input. How does the dependent variable change? What might cause this change? And in this case, and I was going to say it earlier in this video, this is the graph of the distance of a race car from the starting line as it goes around the track. I was going to say a person, but then I realized a person can't run 2 miles in 1 minute. So I'm glad that they cleared up my error. But once again, describe, what is happening now in context here. How does the dependent variable change? So how is the distance from the start line changing, and what might cause this change? And we're going to repeat that behavior, that attempt on slides 4 and 5. Okay, getting into this idea of the period of a function. The period is, in layman's terms, the point at which the function begins to repeat itself. So with the unit circle, you could think about this, or even with like a clock, right? Clock starts at noon. Once we get a full hour, we're back at 12. With the unit circle, once we rotate 2 pi radian or 360 degrees, we're back at our starting point. Functions whose values repeat at regular intervals are periodic functions. That's awkward. There should be an R there. What similarities did you see between the graphs representing these situations, and what are some words you could use to describe the behavior of those graphs? We have a card sort here, where you're going to sort your various cards into categories. And on the next slide, you'll describe those categories. I give you a few categories to select from. If that's not how you did it, totally fine as well. There are no right or wrong answers here. You just need to be able to justify why you linked certain cards with one another. So like I would probably link this. That's just me. That probably put that there. Put this here. That's just because, yeah, I got linear behavior here, I guess, since I put that one over there. I got quadratic or exponential behavior in here. I know that I have some type of trigonometric behavior. But what do you think? Vertical intercepts, range, data type, function type, or something else altogether? And that's where we're going to pause for our initial exploration into the period of a function.